Okay, so we've kind of had the introduction of what molecules and compounds are in the last few videos. In this video, what we're going to focus on is how to identify an ionic compound and kind of what an ionic compound is. So we're starting to get down here towards the bottom of our list. So we have number 7 here, identifying an ionic compound, and then we'll have a separate video for how to name and write the chemical formulas of ionic compounds. So first and foremost, what are ionic compounds? So ionic compounds are also frequently called salts. NaCl, table salt, the thing that we eat every day, is actually only one kind of salt. So any ionic compound can be a salt. Any salt can be ionic compound, interchangeable terms. And I'll likely use both terms along the way to vary what I'm talking about, but ionic compounds are salts, salts are ionic compounds. But what is an ionic compound? Ionic compounds are made of cations and anions held together through their positive and negative attraction, okay? So you know you have an ionic compound if you see a metal in the name or chemical formula, or you see the ammonium ion. So those are going to be our identifiers of cations we can see right away that are indicative of the fact that we have an ionic compound. So if you see a metal or you see the ammonium ion in your compound, you have an ionic compound. So because cations are positively charged and anions are negatively charged, remember, positives and negatives attract. So yeah, when we were talking before, we were kind of talking about protons, electrons. That's how an atom is held together, by that level of attraction. However, anytime we have anything positive and negative, they're attracted to each other. So if we have a cation that is a positively charged ion, and we have an anion that is a negatively charged ion, they want to just hang out together and sit next to each other. So we call these quote-unquote ionic bonds, okay? So they aren't really what we think of as chemical bonds. They're not like that stick in the ball and stick model holding it together. Not the same thing. It's really just this positive negative attraction that holds these ions together, and the way that they're held together is like what we're calling the ionic compound, and from there on out the chemical formula and so on and so forth. So basically what happens is when you have something that likes to form a cation and something that likes to form an anion, if you put them next to each other, the cation transfers its electrons to the anion to make those ions happen, okay? So remember, a cation occurs because you have less electrons than you do protons, so you have a smaller amount of negative charges than you do your positive charges, so therefore you have a positively charged ion. So it can lose those electrons, and when it loses those electrons to form its ion, it gives them to the anion, so the anion can form an ion, okay? So it's like this transfer of electrons. So when we think of chemical bonds really are a sharing of electrons. That's why it's kind of weird to call ionic bonds bonds, is because they're transferring the electrons from the cation to the anion to actually form that ion. We're going to talk about why this happens when we get to chapter 10 in unit 3. We're going to talk about what it means to be able to pull those electrons away. However, all we have to know is that the cation and anion have this transfer of electrons. And once they have that transfer and you have an actual cation positively charged, anion negatively charged, they're two ions that hang out together because of that attraction, and we call those ionic compounds. So ionic compounds are made of cations and anions. Pretty straightforward. So when this happens, we have what we call ill-defined molecules. Okay, so ill-defined molecules. Ill-defined molecules are molecules that don't really traditionally look like what we think of as molecules. So we know we kind of have that picture of water with the red atom with the two little white hydrogen atoms that we looked at when we were talking about space-filling models. We don't really have that here. What we have are lots and lots of the same ions in a repeating pattern together. So we can't really tell which sodium goes with which chlorine. This chlorine, it could be a partner with any one of those 4 sodiums around it, okay? So we don't really know which ion goes with which ion. And that's what I mean when I say it's an ill-defined molecule. It's not really a specific set of atoms grouped together, hooked together in a specific manner. There are just lots of ions that are arranged in this repeating pattern. So that repeating pattern is what we use as the chemical formula. So we've got lots of sodiums, lots of chlorines in here. However, we only report the chemical formula as the overall ratio of sodium to chlorine. So in this case, we have an overall ratio of 1:1 between the sodium and the chlorine. So something cool about ionic compounds is because we are making them out of these anions and cations, they actually break apart into those ions when we put it into water. Most ionic compounds will dissolve in water. We call this solubility. Not all ionic compounds are soluble in water, but most of them are going to be. And they may be soluble in other liquids as well. Remember, in the first lab, we were looking to see if the salts dissolved in water, but we also tested to see if the cobalt chloride, those pretty purple crystals, we tested to see if that dissolved in water and also to see what happened when we put it with ethanol too. So you can dissolve anything into any kind of liquid, but most of the time we're going to see ionic compounds break into those different parts when we put it in water. So I mentioned this a little bit. We have the chemical formula NaCl to represent that ratio of 1:1. We might call that the chemical formula. I will often call it the chemical formula. However, technically though, it's a formula unit. So chemical formula really means that defined, that well-defined molecule. However, here we have ill-defined molecules. So a formula unit just represents that ratio of cations to anions. If you counted all these up, you'd have the same number of sodiums to the same number of chlorines. So therefore, that's why we kind of consider it to be a formula unit rather than a chemical formula. So ionic compound formula units, so that chemical formula, the formula unit, are charge neutral. So under my little face here, they're charge neutral. It's written all over the page elsewhere as well. I'm big. Okay, so ionic compound formula units are charge neutral. So when you have an ionic compound, even though it's made up of these individual positively charged ions, cations, individually charged negative ions, anions, when we add up all of the ions we need to make up that formula unit, we have a charge neutral compound. So the whole overall number of positive and negative charge, when you add it all up, needs to be 0, or you need to have an equal number of positive and negative charges. You could say it that way as well. This is extremely important. We are going to constantly talk about this with ionic compounds. It's not going away. It's going to be here forever. So ionic compounds are charge neutral in their formula units. When you write down the chemical formula for an ionic compound, it has got to be neutral overall. So take NaF, for example, sodium fluoride. So sodium fluoride, I have a picture of it drawn over here to the right for you. So it's a small little sodium cation. Cations tend to be smaller than anions. We'll talk about it as we start to talk about Unit 3. So this is one formula unit. So I've just pictured here one formula unit. If I drew it out, it would have lots of copies of the same thing over and over again to make that repeating solid. So we know right away that sodium fluoride is an ionic compound, and that's because it has sodium in it. Sodium's a metal. If we see something that's a metal, we have an ionic compound. So NaF is the formula unit. So it's, what happened? Sorry. So the sodium fluoride, NaF, is the formula unit. So it's made of repeating patterns of one sodium ion and one fluoride ion together. And actually, NaF is how we get fluoride in our toothpaste. So oftentimes, salts are the most convenient way to deliver anything that we want an ion of. So if we want those fluorine ions, it's really easy to put them with sodium. Sodium fluoride is soluble in water. So anytime we want to deliver ions like that, we can consider if they're soluble or not, and then we can, put it in water. If it's soluble in water, boom, that makes it really easy. So a lot of times we see things, ionic compounds are, again, just great ways to deliver these ions. So a lot of times we see things like these ions and these ionic compounds as ways to present things to us in our life, like sodium fluoride in our toothpaste. So, as we talked about, nomenclature is important. We're going to get into the nomenclature rules for ionic compounds. We have set rules for this, but we'll talk about it as we go along. The one thing that we have to make sure we have here is that we know that we have an ionic compound when we see it. So again, one more time, if you see a name or a chemical formula with a metal in the name or the ammonium ion, you have an ionic compound. Follow the ionic compound rules, okay? Ionic compounds, when we're naming them, are always written cation followed by the anion. Sometimes you have to do something weird, like say what the charge on the cation is, but most of the time you're basically writing the name of what you see and you add the charge if you have to add the charge, okay? So the thing is that some metal cations have set charges that we always know, and some metal cations have variable charges. So they vary. They could have a different charge based upon whatever compound they have formed. So if we hypothetically have one of these cations that has varying charges, when we use our nomenclature rules and we want to write down the name of it, we have to be sure that we include the charge in the name so that we know exactly what we have. Okay, so as I mentioned, we're always going to have some metals that have set cation charges. Other metals will have varying charges. So it's much easier to figure out if it has a set charge or not than anything else. So the metals that you see here on your screen on this periodic table are going to have set charges no matter what compound they are in, so we don't have to worry about telling someone what the charge is because we already know what the charge is. So you don't have to write down the charge on these metal cations, okay? So as you can see on the screen here, these are going to be our alkali metals, our alkaline earth metals, and scandium. So it's kind of easy to remember these guys here because you've got potassium +1, calcium 2+, scandium 3+. So you can kind of remember it go 1, 2, 3 on the top row here of the transition metals. And then the other three that you have to know for sure are aluminum, zinc, and silver. So they start this diagonal starting with aluminum, and aluminum is 3+, zinc is 2+, silver is 1+. So these are the metals with set cation charges that you are responsible for knowing. So anytime you see one of these in an ionic chemical formula, you automatically know the charge. You don't have to think about it. Anytime you see anything else, any other kind of metal in your periodic or on the periodic table in your chemical formula, you got to determine the charge. So these are the only ones you're off the hook for. You know the charge of those. Everything else, you're going to have to spend some time determining what the charge is on that metal, okay? So these are your metals with set charges. And then I'll teach you now how to determine the charge on a cation with varying charges. So we need to determine the charge on metal cations with varying charges, okay? So remember, your charge is based upon the compound that your metal cation is in, okay? So to determine the charge on a metal cation with a varying charge, you have to use the context clues that you get from whatever anion you have, okay? So what you do is you look, you see what your anion is, you look at the subscript on your anion to determine how many copies of it you have so that you can count the total amount of negative charge you have. So in sodium chloride, for example, we know we have just NaCl. So if we just have one Cl, we have one minus charge, okay? However, if we have something like magnesium hydroxide, for example, we'd have Mg parentheses OH in our parentheses 2. So we'd have 2 copies of our negative ion. So our total amount of negative charge is going to be 2 minus in that case, okay? So determine how many copies of the anion you have using the subscript on the anion. You should always know the charge of every anion you encounter because you should have the charge of the polyatomic ion memorized, or it'll be one of the ones from the periodic table that we learned in Unit 1. And you got to use the number of those charges the number of those atoms you have to determine the total amount of negative charge. But remember, ionic compounds, they're charge neutral, okay? So the total number of positive charges needs to be the same as the total number of negative charges, okay? So once you figure out the total number of negative charge, you can use that to determine your total number of positive charge, okay? So you look at your cation, you look at the subscript on your cation, and from there, you have to divide that positive charge among all the copies of the cation you have, okay? I know this seems vague. I know this seems like it doesn't make sense. I'm going to talk you through it. We're going to do some examples, I promise, okay? So the idea here is determine the total amount of negative charge. That is how much positive charge you have. Split that positive charge among every cation you have, however many copies of it you have, and that's the charge on one of your cations, okay? So let's work through some examples. So I have copper sulfate written on the screen there. So we call that copper sulfate, CuSO4, okay? So copper is not an alkali earth metal, or an alkali metal. It's not an alkaline earth metal, and it's not scandium, aluminum, zinc, or silver. We don't know the charge on copper. We never know the charge on copper. We have to figure out the charge on copper, okay? So remember, we use our anion as the context clue. So in this case, my anion is sulfate. So I have one copy of my sulfate. I don't see any parentheses telling me I have more than one copy of my sulfate. So I have one copy of my sulfate. We know that sulfates are an SO4 2 minus, so they have a 2 minus charge. We have that memorized from it being one of our polyatomic ions. So we have 1 2 minus charge. So overall, my amount of negative charge is 2 minus. So my amount of positive charge has to balance that, okay? So I have one copper ion that has to balance all of the negative charge coming from the sulfate. My copper has a subscript of 1, so I have one copper ion that has to balance all of the charge from the sulfate, okay? All of the charge from the sulfate balanced by the charge from the copper. So if my anion is a 2 minus charge, my copper has to be a 2 plus charge in this case, okay? So the sulfate ion has a 2 minus charge, so that means the total amount of positives we have is 2 plus. The subscript on the copper ion is 1, so that ion has to take all of the positive charge. So the charge on one individual copper ion in CuSO4 is Cu2 plus. That's how you determine the charge on the cation. Let's look at our next problem here, okay? So I see I've got Cu2SO4, okay? So if I want to determine the charge on that copper cation, what I need to do is, again, use first my anion as a context clue. So again, I have sulfate. I know sulfate is an SO4 2 minus. I know that SO4 is always a 2 minus. Because it's sulfate. Sulfate is 2 minus. End of discussion. So I see one copy of sulfate, so I have a total negative charge of 2 minus. That means I need a total charge, a total positive charge of 2 plus to balance that out. 2 minus from the anion, 2 plus has to come from the cation to balance it out. However, this time we see a subscript of 2 on the cation, okay? So I have 2 positive total, but that came from 2 different atoms of copper, okay? So now I have 2 atoms of copper that are being used to balance out my 1 copy of SO4. So I have to split that total amount of positive charge evenly across those copper ions, okay? So if I have a total charge of 2 plus and I have 2 copper ions, I must have copper 1 plus. 1, 1, 2 plus, total. So what am I saying here? The sulfate ion has a 2 minus charge always, so we know that we need a total positive charge of 2 to balance that out. However, the subscript on the copper ion is 2. So that positive charge of 2 plus has to be divided between 2 different atoms. So I take my 2 plus charge, I divide it by 2 atoms, so I have a 1 plus charge per each copper atom. So the charge on the copper ion in this chemical formula is 1 plus in this case. So up here we have Cu2 plus in our compound. Down here we have Cu1 plus in our compound. So they have different properties based upon the charge they have. They're going to form compounds in different ways. So it's really important that we know this and we have to figure it out. And we're going to need this information when we actually start writing down the names. This is going to be the first thing we have to figure out when we write the name, okay? So I might ask you to determine the charge on a specific metal cation. However, again, this is going to come back up because it's hidden underneath everything we do in our naming. So it's extremely important that you understand this before you move on to the more complex naming techniques. So this is kind of the base step before you can actually start naming things, okay? I've given you some practice examples here where I want you to figure out what the charge on the ions are. So please go ahead, work through those. Ask me if you have any questions. There's some solutions here as well in your PowerPoint. So you can check out the solutions. If you have any questions, please don't hesitate to ask. I will get those figured out for you. But again, this is an extremely important concept to understand because when it comes to nomenclature of ionic compounds and it comes to actually writing the chemical formula of ionic compounds, we're going to have to be doing this kind of like in the background underneath very quickly. So make sure you have determining the charge on a metal cation figured out and perfected. So this is kind of an introduction to ionic compounds. In the next video or videos, we're going to worry about naming them and writing their actual chemical formula, okay?